let's see. I had an announcement. I just can't quite remember. Let's see.
New problem session times?
Yeah, so there were the new problem session times, and I think, so I talked to my TAs and they were thinking of sort of making the Monday problem session, like you can also go there and do the problems from the problem session, or you could like ask general questions. So it's more of like a office out, like TA office hour / problem session. I don't know if that seems like good to you guys, or I mean, it doesn't really change the procedure, but I don't know. That's an option. So, did anybody go to the problem session yesterday? No. Okay. At least no
I
one.
was planning on going today. I don't know about anyone else.
Okay, yeah. So there is one today. I think it's directly after class, right? The problem session problems are up and the solutions will be posted later. And then let's see. The other thing was that I'm almost done, like, what am I trying to say? I'm almost done grading your exams. Yeah, I've been working on it. I haven't forgotten about that. But I'm almost done, and so I'll probably have them uploaded today, and then you'll get your results back. But overall, I think it was pretty good. I don't know how you guys felt about the difficulty of the exam, like whether it was like good or too hard or too easy. I don't know. Do you have it was good? Perfect level? Okay, sure. Of course, you probably wouldn't say that you want it to be harder, so I guess I shouldn't necessarily.
It's just updating the PDF on Canvas. That's really the hardest part.
Oh, I see. Yeah,
Yes.
yeah. Unfortunately, that's yeah, part of this whole deal with this pandemic. So, okay, let's get started. Let me see. I should open up. Okay. There we go. Okay. Should be working. And then there we go. Oh. Okay, here we go. Okay, so we just have a couple of things to finish up with from last time, and then we'll move on to chapter 3, where we'll start talking about determinants. Okay, so the what we talked about last time was this like rank and nullity, and then we defined the or we stated the rank nullity theorem, right? We also have one more theorem coming from this section, which is called the basis theorem, which we will not prove, but it can be a useful way of thinking about bases and doing a little bit less work to show that something is a basis. So suppose we have H, which is a k-dimensional subspace of Rn. Then two things. We have that any set of k linearly independent vectors will form a basis of H, right? So we do have to know the dimension of H beforehand, right? But if we do, then we just need to find k linearly independent vectors, and we know already that it will form a basis, right? And then the other thing that we can say is that any set of k vectors, so this is of k vectors that span H, we can also say that those form a basis. For H, right?
Can you, I guess, like complete the circle and also say that any set of k linearly independent vectors will also be a set of k vectors that span H?
Right, yeah. So they would accomplish the same thing. Yeah. So it's sort of looking at it slightly differently. Like when we say, okay, we have a set of k linearly independent vectors, we're sort of focusing on the vectors and looking at like how do they relate to each other. And then if they are linearly independent, they'll form a basis. If we have a set of k vectors and we know that all linear combinations of those k vectors will span H, then without saying anything about linear independence, we know that that forms a basis for H, right? So it's sort of taking one of the two parts of the definition, right? Not having to prove both of them. Does that make sense?
Yeah, cool. I guess I was just trying to figure out if you can connect the first part of the first statement and the first part of the second statement.
Right, they're definitely connected. That's true. Yeah.
Cool, thank you.
No problem. Okay, and then the last thing that we need to finish up with for this section is now we have this new terminology for talking about like the for talking about a matrix, right? So we can actually use this new terminology to expand our already very long list of equivalent statements in the invertible matrix theorem, right? So this will be, I'm not going to write down the things that we already have. So this is just to be added on to the list from before. I will type this up into a PDF and post it so that you'll have everything in one place, but I haven't gotten to that just yet. So this is the invertible matrix theorem continued. And so always A is an n by n matrix, right? And the following statements are equivalent. Okay. Let's say the following are equivalent to the statement that A is an invertible matrix. Okay. So first of all, the columns form a basis of Rn. I think we may or may not have stated, no, I don't think we did. So the columns of A form a basis of Rn, which is essentially the same thing as saying the columns of A span Rn, right? We
Is
all,
that the same thing as saying that columns of A are linearly independent?
yeah, so it's all of those things combined. Yeah, exactly. So a basis is just a set of vectors that span your subspace and also are linearly independent. So it's sort of like combining those two things. Right. Okay, we also talked about the column space and null space. So another equivalent statement is to say that the column space of A is equal to Rn. Or the dimension of, or wait, what did I use for this? Rank, right? This is strange. Okay, yeah, we'll just say, or the rank of A is equal to n, right? Which is essentially saying the same thing. And then in terms of the null space, right? The null space is all of those vectors that satisfy, oh, oops, sorry. Okay, the null space is all of those vectors that satisfy the homogeneous equation, so that AX equals 0. And so if our matrix A is invertible, this will have only the trivial solution. So the null space of A is going to just contain the 0 vector, right? Okay. And then also the nullity. So that is the dimension of the null space of A is 0. Yeah, 0. There you go. Okay, so this is just going to be added on to the invertible matrix theorem. So this is just a new way of like talking about the same ideas that we've been talking about this whole time. Okay, so moving on, we get to start talking about determinants. So we've already defined determinants for 2x2 matrices, right? But that's the only size that we were able to define the determinant for. So we're going to get into some of the higher or the larger matrices, right? So first of all, these determinants are only defined for square matrices. Right. And what they do is they assign a number to a square matrix. So we could actually think of the determinant as a function, right? Where the determinant acts on the space of square matrices, and the output is always a real number, right? So it's just a function from the space of square matrices to R, right? And it's defined in a particular way. So I won't, define it any further than this, but this is just to say that we could think of this as a function, right? Okay. And then our notation, we can either write det of the matrix A, or we just use these vertical lines, and that denotes the determinant as well, right? And when we do this, you'll see we drop the square brackets around the matrix. So instead of putting lines and then the brackets to denote the matrix, we just drop the brackets. So just the lines. And there'll be plenty of examples of that. So, okay. So what we're going to do is define first 3x3 determinants of 3x3 matrices, and then we'll move on from there. So this definition is it is recursive. How do you say this? Right. So I would say the determinant acts on the space of square matrices, and like sends it to R. I guess that's how I would put it. Does that answer your question? Yeah, okay, cool. All right, so this definition is recursive in the sense that we use the definition of the determinant of 2 by 2 matrices to define the determinant of 3 by 3 matrices. Oh, okay, determinant of 3 by 3. And then we use 3 by 3 matrices to define the determinant of 4 by 4, and then so on, right? So it's recursive in that we use the previous definition to define the next step up, right? Okay. So let's look at a 3 by 3 matrix. We'll just say it has entries A, B, C, D, E, F, G, H, I, like that. And we want the determinant of this guy, right? And the idea is we start with this first entry right there. And our determinant will be A, that first entry, times the determinant of the smaller matrix, which will form by just crossing out the row and column where A is. So the row and column containing A, right? So like I've drawn here. And what's left is this smaller matrix, right? A 2 by 2 matrix. So it will be A times that 2 by 2 matrix, E, F, H, I, right? And that's the first term that will define our determinant. And then next, we move to the next entry in the first row. So that will be, I've already like drawn all over this matrix, but that'll be that entry right there, B. And we're gonna alternate signs. So since the first term was positive, the second term will be negative. And then we take B and we multiply it by the determinant of the 2 by 2 matrix, which is formed by crossing out the column and row that B is in. So for this case, we still cross out the first row and then we cross out this second column. I'm not going to do that because then this would get really messy. But what we'll be left with, if we do that, we cross those out, we'll have D, F, and G, I. So that 2 by 2 matrix. And then we move to the last entry in the first row. That's C. Again, we're alternating signs, so this one will be positive. And then we cross out the row and column that C is in, and we're left with the determinant of the matrix D, E, G, H. Right? And then we know how to compute these smaller matrices, right? So remember, it's like this multiplication of the diagonal things, right? And we subtract those two. So we subtract the off diagonal, I guess you could think of it as, from the main diagonal. Okay, so maybe I'll write that part out. So in the end, we get A times this minus B times D times I minus F times G plus C, write this one down here, times D times H minus E times G, like that. And then be careful that you're, being careful with your negative signs because that can, become a problem.
Just a question. Is there a particular reason why the signs alternate? Or is it just by definition?
So let's see. There is a reason, but it's hard to motivate, right?
One satisfying explanation that I've seen for the determinant is that if you just start with the standard basis vectors and create the unique parallelogram formed by those basis vectors, then the determinant gives you how much the area of that parallelogram is scaled. So it's kind of how much it stretches or moves space. But writing out all those calculations is like really weird. So it just ends up in this like large formula that you just kind of have to memorize.
Yeah, basically, yeah. So yeah, there is that like geometric interpretation of it. There's also a relationship between this, the determinant, and our row operations, which we'll talk about. But yeah, that's an interesting way of thinking about it. Maybe I'll look into it, see if I can, maybe like condense it down into something we could do in like the next class. But yeah, okay. So yeah, maybe I'll make a note here. So these do alternate signs. Right? Okay. So this is our definition for a 3x3 determinant. I'm going to move this down just a bit. Okay, come on. There we go. Okay, and then like I said, we use the 3x3 determinant to define a 4x4 determinant. So for a 4x4 matrix, we would have the determinant of, so just filling these in, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? We will get, so again, expanding using the first row, we would get A times the determinant F times, or sorry, not F times G, F, G, H, J, K, L, N, O, P, right? Then we alternate signs, so we get negative B. Here we would get E, G, H, I, K, L, M, O, P. And then two more terms, we get C, E, F, okay, E, F, H, I, K, nope, I, J, L. There we go. And M, N, P. And then lastly, we have negative D times, I'll move this over a little bit. We get E, F, G, I, J, K, M, N, M, N, oh, like that, right? Okay, and then we break those down using our definition of the determinant for a 3x3 matrix. And then, so we'll get all of these separate terms for each of these pieces that we have. And these pieces actually have a particular name. These are called cofactors. So this guy right here, this is called a cofactor. Each one of them is, right? And then, right, I'll say more about that, but not just yet. Oh, I will say that, okay, so this is called a cofactor, and the whole thing we refer to as a cofactor expansion.
So those constants A, B, C, those are cofactors.
Oh no, not the constants, but the this thing right here, like,
Okay.
yeah. Okay, so let's do an example of computing a determinant, right? So here we have, we'll do a 4x4 determinant. So with rows 1, 0, 0, 1, 1, 3, 0, 1, 1, 2, 1, -1, and 1, minus 1, 3, 0. Okay, so for our first entry, we have a 1, right? That's going to be positive, and then we multiply that by the determinant of the 3 by 3 matrix that we get by eliminating the row and column that that 1 is in. So we would get the matrix 3, 0, 1, 2, 1, minus 1, minus 1, 3, 0, right? And then luckily the next two entries are both 0. So we're going to get 0 times some determinant. So we don't even need to worry about writing that part down, right? Those are going to be zeros. The last one, we do have a 1, so we need to include that. And it's going to be negative, right? So because remember, we're alternating signs. So moving across, we start positive, negative, positive, and then negative for the fourth entry. So we get negative 1 times the determinant of 1, 3, 0, 1, 2, 1, 1 minus 1, 3, like that. Okay. And then we just need to deal with each of these two determinants separately. So for this first one, we would get 3 is our first entry in the first row, and then we multiply that by the determinant of 1 minus 1, 3, 0. And then the second entry is 0, and the third entry, which is again positive, is 1, and we multiply that by the determinant of 2, 1, minus 1, 3, like that. So that's the determinant of that first 3 by 3 determinant. Okay, and then we get a negative, oh, oops, we're adding this to that first part. And then our first term, or our first entry is 1. We multiply that by the determinant of 2, 1, minus 1, 3. Then we get minus the second entry is 3. We multiply that by, so remember we're crossing out the row and column that 3 resides in. So we get 1, 1, 1, 3. And then the last entry is 0, so we don't need to include that one. And it's just a matter of simplifying things. So 3. And then this 2 by 2 determinant, this first one is 0 minus negative 3. So it'll be 3. I guess I didn't need to write those so big. Minus 3. There we go. And then the second determinant will be 6 minus negative 1. So it'll be 7. And then we get minus, this one is 6 minus negative 1 again. Interesting. What did I mess up here? Oh, yeah, you could cancel them now, or you could compute them. Yeah, you're right. That's fine. Either way is fine. And then, okay, we get plus 3 minus 1, so 2. So that is negative 9 plus 2, so we get negative 7.
Me. You need to do the multiplication by 3 on the outside of that final determinant.
On the outside of which one?
The final one, so it's minus 3 determinant 1, 1, 1, 3.
Yep. Thank you. Okay, so this was 2. We get minus 3 times 2. Right. Okay, so then that's negative 9 minus 6, which is negative.
Oh, sorry, I broke it. It's negative on the inside of the parentheses. Yeah, sorry, my bad.
No, you're fine. Okay, so that's 3. Negative 3. Right? We agree? Okay, Right, so we got lucky in the fact that there were 2 zeros in that first row, so this wasn't too terrible, but if we had non-zero entries along the first row, it can get, kind of large when we're doing these. Okay, so there is something that can help with these sort of calculations. So in our definition of the determinant, we used the first row for the cofactor expansion, right? We used the first row and then we expressed everything else, our cofactors, in terms of like what was left when we cross out the row and column of the entry that we're starting with or we're using. So let me see this. In the definition of the determinant, we used the first row for the cofactor expansion. In fact, we can use any row or any column. We can use a row or a column, right? Right? Okay. But we need to keep track of those alternating signs. So the way that this will work is, do this down here. So if we have our arbitrary matrix we want to compute the determinant of, the way that the signs work is, well, like we said, it's alternating. So we know that across the first row, what we did was we started with positive, we go negative, then positive, then negative, and so on, right? And then, so it will work the same way in each column. So it will start in the first column, we start with positive. So next it will be alternating. So negative, and then positive, and then negative, positive, and so on. And then since the second row should also be alternating and it starts with a negative, then we have positive, negative, and so on. So we get this sort of matrix that describes the signs, right? So. And then, so however large your matrix is, this is, how it will go. This is what it will look like. Right. So if you were to use, say, the second row to do your cofactor expansion, you would start with a negative in front of that entry and do your cofactor expansion that way and alternate signs starting with negative and then positive, negative, positive, and so on, right? Okay, and then one thing that is good to know is that the ijth entry, so remember that refers to the ith row jth column. The ijth entry has sign -1 to the I plus j. So if I plus j is even, then the sign is positive. And if I plus j is odd, then the sign is negative. Is 15? Oh, so you mean?
Yeah, I typed this in the software and then I calculated the determinant and it displayed 15 instead of -3.
I see.
See if we use 1.
Oh, this should be positive. Yeah. So no, never mind. That's not true. This is, yeah. No, it should be positive. It's negative. Yeah. Okay.
That would be 15.
Okay, there we go. Okay, so good. We agree. Okay. Right.
Sorry. Oh, okay. Never mind.
Okay. So you don't have a question?
No, I was confused, and then I figured out why it's 15.
Oh, okay. Cool. Okay, so right, let's go ahead and use this idea to do another example, right? So remember that what helped us out in the first example was those two zeros in the first row. So generally when you're choosing a row or column to do your cofactor expansion, you want to choose the one with the most zeros, right? Because that will be the least amount of work. So say we have the matrix, I'll just write it down, this guy here. Okay. So we want this determinant here. And so we can see that that second row there has 3 zeros. So we're only going to have one non-zero term in our determinant. So that's definitely a good choice for our cofactor expansion, right? So starting with the second row, the first term will be negative. So that means this non-zero term, the sign in front of it is going to be positive. So we get positive 2 times the determinant of the matrix 1, 2, 1, negative 1, negative 2, 1, and then 1, 4, 1. Right. And then there's no like clear winner for this expansion here for the 3 by 3. So we can just use the first row to do that. So we'll get negative 2, 1, 4, 1, that 2 by 2 determinant, minus 2 times, maybe I'll move this over a little bit. 2 times negative 1, 1, 1, 1, and then plus 1 times negative 1, negative 2, 1, 4. Right, and then it's just a matter of computing these. So negative 2 minus 4 would give us negative 6. Negative 1 minus 1 would give us negative 2. And negative 4 plus 2 would be negative 2. So this would be negative 12 times 2. Right?
Wait, so it's -6. Wait, wouldn't the inside parentheses be like, let's see, negative?
So you have -6 plus 4 minus 2.
Okay.
So that would be
Plus-
-8.
I see. Negative 8. Wait, really?
No.
Negative 4 in there,
Sorry,
and
that's not
negative
right
8 is the
either.
final answer.
Yeah,
I
that'd be
can't do math.
inside is a -4, and multiply by 2, you get -8.
Wait, so at the end you get negative 8.
Yeah, so then the
Yeah.
inside parentheses is -4.
I'm so sorry.
No, it's totally fine. That's what I got when I did my notes. So that seems pretty promising. We'll just say it's negative 8. Okay. Negative 6 plus 4. Yeah, I agree. Okay. Cool. So this is how we can do this. And let's just do one more example where we use the column to expand. So
And this can get already tedious with the bigger matrices.
yeah, it does get really tedious, unfortunately. So -1, 3, 0, 0, 5, 2, 1, 4, -3, and 1, 0, 5, 0. Okay, so in this case, the column or the row or column with the most zeros would be the second column. So if we're considering all rows and all columns to do our cofactor expansion, this second column has 3 zeros, which is the most out of all of them. So we're going to use that to do our expansion. Now, if we want to figure out what the sign should be on this one that we're going to use, on only non-zero entry in that column, what we can do is we can start from, we know that the first entry, the one in the first row, first column is positive, and then we can just like skip to that entry. So we know that it alternates. So this will be negative. And then if we move down to the next row, so like moving down in the column, we know that the column also alternates. So this will go positive, negative, and then positive, and then this guy will be negative, right? So we can just like move to that entry, and then we'll know if we alternate as we move that the sign on that guy will be negative in this case, right? So it'll be -1 times the determinant of, so let me just cross this out. So we can see that we'll get 1, 2, -1, 3, 0, 5, 1, 5, 0.
I've been doing a technique to keep track of the zeros. I don't, where I just write out literally +0, -0 to help me keep track of the terms, just
Yeah.
because this is new for me.
Yeah, no, that's totally fine. And yeah, if that helps you, then I suggest you do, yeah, whichever way is most, helpful for you. Okay, so we just have this one 3 by 3 determinant. What do you want to use to expand it? Since there's like a few different ways we could do this. Anybody have an opinion?
Let's do, oh, sorry, go ahead.
I was gonna say use the second column.
Use the second column. Okay, yeah, let's use the column. So this guy right here. So we have that the sign on this column, let me just write it in here. So this goes positive here, so it'd be negative, positive, negative. So we'll have our -1 out front, and then we'll have -2 times the 2 by 2 determinant, 3, 5, 0. We'll have a 0, and then we'll have -5 times the 2 by 2 determinant, 1 - 1, 3, 5. Okay. And then it's just a matter of simplifying, so we can just do 2 times 0 - 5 plus 5 times 5 plus 3, 8. Yeah, so it should be 30.
Yeah, that sounds.
Okay. So we usually stop for the quiz around what time? Do we actually go until 2, or do we go until
We go till 150.
150? Okay. Okay, so we'll stop at 1:30 and we'll do that. Okay, so there are some things that we can use to, some little shortcuts that we can have. So one thing is if we have a triangular matrix, then the determinant, so this could be upper triangular, lower triangular, doesn't matter. Just if it is triangular, then the determinant is just the product of the entries along the main diagonal. So it's just A11, remember this refers to the entry in the first row, first column, times A22 times A33, all the way up to whatever size your matrix is, ANN, right? And why might this be the case? Well, we can just look at a particular situation and this kind of generalizes to all triangular matrices, but let's just consider a n by n upper triangular matrix, right? So say we have A is A11, A12, A1n, and then we have zeros here, right? So this is A22, 0, 0, and then right, like this, and it ends at ANN, and we get right zeros along here. Okay, so this is sort of what an arbitrary upper triangular matrix would look like. Let me line these up. And if we were to do our determinant, the the row with the largest number of zeros is going to be that last one, right? Because we know it's got zeros all the way along up until you reach the last entry, right? So if we use that to do our cofactor expansion, then the determinant of A will be equal to that last term, ANN, right? The sign on it, actually, we should probably deal with the sign first. So we know that since this is in the nth row, nth column, the sign on that is going to be -1 to the n plus n, right? Remember the ijth entry has sign -1 to the I plus j. So we know that this is -1 to the n plus n, ANN. But luckily, this is -1 to the 2n, so it's an even number, meaning that this is going to be positive, right? So it's just going to be 1 there, and then we multiply this by the determinant of the n minus 1 by n minus 1 matrix, which will be, so we'll just lose the last row and last column, and we will still have a triangular matrix, right? Because eliminating those, the last row and last column doesn't change that. So now we'll go from here to a n minus 1. I have to squeeze this in here. So this last term will be a n minus 1, n minus 1, right? We get this, this matrix. And then we do the same thing where we want to expand along the bottom row because it has all of those zeros. And then what will happen is we get ANN times the, here we get -1 to the n plus, or sorry, n minus 1. N minus 1 plus n minus 1, a n minus 1, n minus 1 times the determinant of, now we have an n minus 2 by n minus 2 matrix, which is still triangular, and we just keep going in this fashion. So notice that this is again just 1 because it will be an even power of -1. And so each time we pop off one of those diagonal entries as we go. So you could see that if we just continue until we get to A11, we just get ANN times AN minus 1, n minus 1, times all the way down to those A22, A11, right? So that's just the product of all of the entries along the diagonal, right? Okay, so hopefully this all makes sense. And you can see that this would work the same way for a lower triangular matrix. We would just use the top row each time to do our cofactor expansion. Okay, so note that just from this, we know that the determinant of the identity matrix, which has ones along the diagonal, so it'll be just the product of all of those ones. So that determinant will be 1 for any size matrix, any size identity matrix, that is. And also, oh, okay, so this is somewhat unrelated. So, so on another note, also if A has a row or column of all zeros, then the determinant of A will be 0. So this should be not too hard to justify to yourself. But if you have a row of all zeros, then you could expand along that row. You get all zeros, well, a sum of zeros, and that would be 0, right?
If you had a diagonal zeros, that wouldn't be true though.
Oh, that's interesting. If you had diagonal zeros, then no, not necessarily. Because if you, I think, like fill in everything else with ones, you would still get something non-zero. Would you? I don't know. This is interesting.
Wouldn't it be 0? Because the mean diagonal. Oh, wait.
Let's see. So
So like each of those.
I'm gonna put it into Symbolab and see what it comes up with.
okay.
So that way you don't. I didn't mean to like stop you mid like
You're fine.
venture.
That's an interesting question. I don't know. I'll have to look at it for a second, but right. Let's see. We have, yeah, let's keep going. So this is true that if you have a row of all zeros, that it will be 0. Then also there is a relationship, I think I alluded to this before, but there's a relationship between determinants and our elementary row operations. So it's not going to be the case that every elementary row operation will not change the determinant, right? So some of them do change the determinant. The one that does not is our replacement. So doing a row replacement on a matrix A, maybe, yeah, row replacement on A does
It's
not.
not 0. I'm just letting you know.
Okay, okay, that's good to know. Row replacement on A does not change the determinant. So remember, row replacement is the operation where we take a row and we replace it with that row plus a constant times another row, right? However, the other two will change the determinant, but in a particular way. So we will know exactly how they change the determinant. So if we scale, so scaling a row by a scalar C will multiply the determinant by C. So that's a predictable change, right? So scaling a row by C will multiply the determinant by C. And the other, or the last row operation that we have is the swapping of two rows. So swapping two rows will multiply the determinant by -1. So it changes the sign. Multiplies the determinant by -1. Okay. So we can see this in action. So just looking at a simple example, time for this, yeah. So we'll look at a 2x2 determinant because those are easy to compute, right? Or rather a 2x2 matrix. So let's look at 2, 1, 1, 4, right? This matrix. And so we're going to do row operations and then compute the determinant each time and see how it changes, right? So to start off with, the determinant of this guy is 8 minus 1, so 7, right? And let's just row reduce this. So the first thing we could do is swap the rows, right? So we get a 1 in the first entry. So let's do that. So swap row 1 and row 2. If we do that, we get 1, 4, 2, 1. And according to this, if we swap two rows, it should multiply the determinant by -1. So if we recompute, maybe I shouldn't use A. If we recompute the determinant, we started with 7. Now we get 1 minus 8, so we get -7. So it did change in the way that we expected, right? Next, so if we are row reducing this matrix, we would want to do a replacement. So we would want to take row 2, replace that with row 2 minus 2 times row 1. Right, so our first row will not change. And our second row will become 0. We'll get -8 plus 1, so -7. Is that right? Yeah. Okay. And then when we compute the determinant, we get -7 minus 0. So again, the determinant is -7, so it did not change. So that's good. Next, what we would want to do is scale that second row by -1/7. So take -1/7 times this row 2, right? Which will just change this into a 1. And now this determinant is now 1, right? So we just took that previous determinant and multiply it by the scale, which is -1/7, and we get 1. And then to finish this off, we would just take row 1 and replace it with row 1 minus 4 times row 2, which should not change the determinant. And it does not, because this is just the identity matrix, which has determinant 1. Right? Okay. So it is good to know that this is something you can do. So you can apply row operations to find your determinant, right? And just keep track of those row operations. Thank you. Yes, we should do the quiz. But yeah, we have to keep track of those row operations so that we know how to adjust the determinant that we get of the matrix that we get at the end, right? So we'll talk more about that next time, but yeah, we should move to the quiz, which I need to make available. So give me 1 second for that.